So you already know that over time, bones grow in girth and length. As we develop from infancy to adolescence, long bones get longer and thicker. These changes are mediated by two processes: appositional growth, which accounts for the thickening of bone, and interstitial growth, which accounts for the lengthening of long bones. In addition to increasing girth and length, as bones develop, they also undergo subtle changes in shape in response to changes in stresses. These changes are mediated by coordinated activities of osteoblasts and osteoclasts and is referred to as remodeling. The pictured X-ray is of the distal forearm and wrist. Based upon your understanding of the end result of the endochondral ossification process, you know that the X-ray is of a still growing bone. X-rays only reveal bone. You will notice it appears that the very end of the bone is separated into a smaller segment. Of course, this is not the case. The space between the two bone segments is filled with cartilage. It is the epiphyseal or growth plate. The calcification process, similar to the endochondral process, takes place adding bone to the distal end of the proximal portion, pushing the distal section distally, resulting in increased length of the bone. A micrograph of the growth plate reveals the interstitial growth process. The reserve cartilage is distal and calcification works its way proximally. Appositional growth is mediated by coordinated activities of groups of osteoblasts and osteoclasts known as remodeling units. Remember, the periosteum is the protective and nutritive connective tissue that lines the external surface of the bone. Osteoblasts are located between the periosteum and the external bone surface. Osteoblasts lay bone matrix down on the external surface of the bone, increasing the girth of the bone. Osteoclasts exist on the internal surface of the bone. Osteoclasts remove bone matrix, countering the action of the osteoblasts. So, while the osteoblasts lay down new bone on the external surface, osteoclasts remove bone from the internal surface. The coordinated activities of these two cell types facilitate the remodeling and controlled growth of bone. Bone tissue plays a significant role in maintaining calcium blood levels. The body contains about 1,200 to 1,400 grams of calcium, of which 99% is resident in bone. Only 9.2 to 10.4 milligrams per deciliter circulates in the blood plasma. Changes in blood calcium levels cause significant changes in, amongst other things, nervous and muscular tissue, leading to spasms, muscle weakness, and emotional disturbances. Calcium levels are controlled by a negative feedback loop. The parathyroid gland acts as the receptor sensitive to decreasing levels of calcium. It responds to low levels by secreting parathyroid hormone, or PTH. Parathyroid hormone has the effect of increasing osteoclast activity, stimulating the kidneys to decrease calcium excretion, increasing vitamin D production, and inhibiting osteoblast activity. The result of these effects is an increase in calcium blood levels. More so in children, the thyroid gland is sensitive to high levels of calcium. When levels are high, the thyroid secretes calcitonin. Calcitonin has the effects of inhibiting osteoclast activity and stimulating osteoblast activity, thereby lowering calcium levels. Even though bones are specialized for strength, humans still manage to fracture bones. From extreme sporting and recreation activities, falls and accidents, motor vehicle accidents, and metabolic disorders, bone, even with its specializations, are at risk for fracture. Bone heals by a regenerative process, meaning bone tissue heals with bone tissue. The first step in the healing process is the formation of a hematoma or blood clot to stop the bleeding that results from the ruptured blood vessels. After a few days, a soft callus or fibrocartilaginous callus forms that connects the two fractured ends of the bone. Within about a week, bone tissue begins to infiltrate the soft callus, forming a bony or hard callus. Almost simultaneous with the development of the hard callus, remodeling units begin remodeling the bone, attempting to return the bone to its pre-fractured form. This pictured X-ray reveals a humeral fracture. This X-ray reveals the same fracture after about 3 weeks. The hard callus is evident. This callus will undergo remodeling for weeks and perhaps months after the fracture, with the attempt to return the bone to its pre-fracture form.